Okay, in this video I'm going to look at this simulation to just look at properties of two-dimensional projectile motion. Okay, so to show you how the simulation works, we have a cannon. We have a little statue that's wearing a pair of pants here. There is a vertical line to mark where the cannonball starts, and there's a horizontal line which indicates what the initial height of the cannonball is. Notice that the target that they have over here is below the initial height of the ball. A lot of the analysis we're going to be looking at, a lot of the properties we're going to be looking at, we need to look at what happens when the ball starts and stops at the same height. Okay. So let's just use it as it's set up to begin with and show what happens. As we fire, you can see at the X's it changes the range and the height, which is nice. So that's what this looks like. Right? Notice the box over here has the air resistance turned off. Right? So from that, what really matters is how fast does it fire, the initial speed, and at what angle. Okay? We're using just the basic projectile. There is a bunch that you can choose from. I find they're fairly amusing. So for example, if I choose to fire a piano, looks kind of goofy. The piano comes up, comes down, and goes splat. On the other hand, if I fire the adult human, he goes up, he comes down, and he ends up with a headache. Now, how can you have a piano go splat and an adult human end up with a headache? I think it's kind of silly. Okay, so we're going to erase those, get rid of all that, and just go back to the initial, what it looked like to begin with. Okay. So there we go. Okay. Now, one thing to notice. Currently I'm firing at an angle of 80 with an initial speed of 18. If I choose an angle that is symmetric about 45 degrees, so that in this case would be an angle of 10. Right? Okay, it said score because technically the projectile hit the target over here on the ground. But what I want to look at is this point where I'm looking at the same height that I fired initially at. Right? And the 80-degree curve and the 10-degree curve both happen to hit that mark. Right? So for angles that are symmetric about 90 degrees, or around 45 degrees, they go the same distance, assuming we can ignore air resistance. So let's just erase these two and do another set, just because. So if I choose a 30-degree angle and fire it, I'm actually going to erase that, slow it down a little bit, just so that we stay on our line. Oh, maybe that was a little too far. One more time. Ah, perfect. Symmetric about 45. I want to go to 60. And again, they cross at our initial height. The other thing I want you to look at is see the angle that it goes up at versus the angle it comes down at. Hopefully you notice that they're equal. That means that whatever the velocity is here in the vertical direction, the velocity here will be the same magnitude, the same size, but in the opposite direction. Okay? Now, I don't know what the vertical velocity is here just based on these numbers, because all it tells me is the total velocity, both vertical and horizontal combined, and the angle. I could calculate them, but we're not going to for this class. I don't want to bring the trig into it to do that. So, for angles symmetric about 45, I go the same distance. Probably shouldn't surprise you then that 45 gets me the longest distance, right? So remember, I have a curve here for 30, a curve here for 60. Let's try something in between 30 and 45, maybe 37. And something a little bit bigger than 45, let's try 48. So, yeah, it went just a little bit less far. Just a little bit. Right? So 45 degrees will get me to go the farthest. Now let's take a minute, erase those. I'm going to put one back on. Let's see, let's try the 60-degree curve again. Up it goes. Okay. Now what I want to do is I want to turn air resistance on. And I'm just going to use it as it's programmed here and see what that does to my projectile's motion. Right? At the beginning, the one with air resistance follows the no air resistance curve fairly well. But eventually that starts to deviate and ends up I go less high and less distance. Okay? That means that my red curve is no longer symmetric, right? And is a much harder beast to deal with, if you will. Right? The other thing to notice, I'm going to go back to a 45-degree angle here. Oop, I'm going to erase that really quick. 45, fire it. Here we go. Now if I turn air resistance back on, just as we saw before, it does go less high and not as far. But now let's try decreasing the angle and see what happens. Almost the same distance. A little bit less. Okay. So it looks like for the conditions we have set up, for the mass we have, for the diameter we have, 45 does appear to still give the longest distance for small angles. Let's go to the other side. Again, a little bit less. Depending on how these are set up, 45 degrees may not still give the longest distance. That's just a tidbit of information because it's kind of fun, and I'm not going to test you on it or anything like that. Okay. Remember, I gave you the link to look at this particular simulation on your own. Feel free. Go in, play with it, look at it. It probably would be more beneficial for you to do it than to just watch me do it and talk about it. And on that note, I will end this video.